Welcome back to our series on multivariable calculus. In this episode, we're going to talk about finding volumes using cylindrical coordinates. This will still involve a double integral, but now instead of integrating over x and y, we'll be integrating over r and theta. These 3D functions will feature z as some function of r and theta. Frequently, the initial problem will not feature that. It might actually feature a multivariable function in x and y. So the first thing we have to do is review conversions from rectangular to cylindrical coordinates. Because if your initial function is not in this form, you're definitely going to have to put it in this form. In order to do that, remember the conversions that r squared equals x squared plus y squared. Remember that the tangent of theta is equal to y over x. Keep in mind that x is equal to r cosine of theta, and that y is equal to r sine of theta. Armed with these conversions, you'll be able to move any z function of x and y into one that's in r and theta. The next thing you have to worry about are the limits of integration. Let's talk first about the theory behind this, and let's sort of build the standard integral that'll find these volumes for us. Let's first begin with the idea that we'll have some sort of a polar function in the r theta plane, which remember replicates the xy plane. Well, within that plane, of course, we're going to have these broad wedges, similar to what we did in finding the area in polar coordinates in a plane, except we're not going to integrate over these area elements. The difficulty there would be the height of the function along this element would vary tremendously, and so we have to break it down into smaller pieces. Instead, we're going to draw little bands across it, and then we're going to represent these as little towers, which have the top of them equivalent to the function of z. And of course, the sides are going to be defined in terms of our planar polar coordinates. So here's what the sides of this little rectangular prism are actually going to look like. First, the height. The height is just going to be f of r and theta. And that's really what we'll be integrating. This is the reason why we can't use this big triangular wedge, because this value will vary across it. And so we have to use these little tiny volume units that have a cap of exactly the height at r and theta. Okay, what's this unit then here? Well, this is a portion of the radius, so that will be dr. And then the outer dimension here, this is the arc length, so that's going to be r d theta. And so when we build the integral will actually be built out of volume being equal to a double integral. The outer integral could be theta, the inner integral could be r, and then what we're integrating is f of r theta, r dr d theta. And yes, it does introduce an extra r into the integral, but that's imperative because the outer dimension, that is one of the sides of this little, well, I'll call it a rectangle. It isn't really a rectangle. Remember, these are arcs on the inner outer edge, and these are radiuses on the top and bottom edge. But nonetheless, it's very much like a rectangular base, and its dimensions are dr by r d theta because it's based on arc length. So that's where the extra r comes in. So keep in mind that when you integrate your functions, you're always going to be multiplying that function by an extra r in order to do the volume. Now, finding your limits is exactly the way they would be had you been just doing a traditional volume. Instead of looking for the area of the rectangle in the x and y direction, you'll be looking for the limits in theta as the polar graph is being drawn in the plane. Just like we looked at in the previous episode, make sure that you're not over or underestimating the amount of theta you'll need in order to draw the complete graph you're after. And in the same way, the radius. Mostly the radius is pretty straightforward because you're going to move from inside to the outside. Sometimes the radius is functionally based. Sometimes the radius is a constant. And in the same way that we sort of played with the shape of the base by controlling the radius, that it was larger or smaller than a certain value, we can do the same thing here. So sometimes you'll be finding the area between two hovering curves. Sometimes you'll be finding the area where there's an outer and an inner function actually in the plane. And all of those can be handled by simply manipulating your limits of integration. That is, you'll be going from your inner R to your outer R. You'll be going from one theta to another. So it tends not to limit what the function is that you're integrating, unlike when we looked at areas in a plane. Instead, it'll just really mess with the limits of integration that you're using. So other than the building of the integral and using polar notation, these double integrals are not functionally very different from what we did in rectilinear coordinates x and y.